So we start the session today with Daniele GREGORIS, Understanding Gravitational Entropy of Black Holes, and a new proposal for via curvature invariants. Please, Daniele, go ahead.
Good morning, everybody. My name is Daniele GREGORIS, and I come from Zhengzhou University of Science and Technology. In my talk, I will try to advance our understanding of gravitational entropy of black holes, and I will adopt a mathematical technique from differential geometry, which is based on some curvature invariance approach. We can introduce a notion of entropy from many different perspectives. For example, from thermodynamics, in which entropy is the arrow of time. And in this case, we say that entropy is a quantity which cannot decrease in time. This is the approach followed by Clausius. We can introduce entropy as well from statistical mechanics as a measure of disgregation and as a quantification of a number of possible different microscopic realizations of the same macroscopic system. This approach was followed by Maxwell, Boltzmann, and Gibbs. We can introduce entropy also in information theory, again from a probabilistic perspective. And this approach was followed by von Neumann, Shannon. So one question that we want to answer is whether we can assign a notion of entropy to the gravitational field. And following the pioneering works of Hawking and Bekenstein, the answer is yes. In fact, in the paper, The Four Laws of Black Hole Mechanics by Bardeen, Carter, and Hawking, it was noticed that the area of a black hole event horizon have a close analogy with entropy. And in a previous paper, in fact, Hawking has demonstrated his remarkable never decrease area theorem for black holes. And so, according to Hawking, black hole entropy is given by the horizon area of a black hole, and taking into account also the never decrease area theorems, this is the thermodynamical approach to the notion of entropy. On the other hand, more or less in the same year, Bekenstein claimed that the black hole entropy is a Shannon information entropy. So according to Bekenstein, the entropy of a black hole is related to the amount of information hidden by the event horizon. And remarkably, the same result as Hawking was obtained. Black hole entropy is horizon area, also following this approach. I wrote remarkably because, as you can see, completely different physical arguments were used. But as we know from college physics, to show that the different notion of entropy I previously mentioned are equivalent is not so simple. Then it has become possible very recently to use gravitational data to confirm that in the merging of two black holes, the area of event horizons is indeed not decreasing. So we start having that these are not only mathematical theorems, but they are physically rooted. So the question is, what is this entropy actually referring to? Following again another paper by Bekenstein, we see that the black hole entropy is the entropy of a pure gravitational field, and it should not be confused with the entropy of a matter field outside the event horizon. For example, Schwarzschild is an empty space-time, but nevertheless it comes with a non-zero entropy. And in fact, quoting John Wheeler, we can say that in a general relativity, we can have a mass without having matter. So we wanted to assign a notion of entropy to the mass rather than to the matter. So from college physics textbook, we know that entropy is an extensive variable, and it is expected to scale as the volume of a physical system it refers to. Instead, we have been learning so far that for a black hole, entropy is instead scaling as with the area of the horizon, and therefore it is important to deepen the physical understanding of this entropy law. Another possible way of reinterpreting the Hawking never decrease arrow theorems is to follow and to adopt the language of Christopher Ruffini. They introduced the notion of reversible versus irreversible transformation in black hole physics. And they introduced as well the notion of black hole irreducible mass as a quantity of energy which cannot be extracted from a black hole by using the reversible transformation. And they show, by adopting again other physical approaches, so we invoke the particle-antiparticle creation mechanism, and then we track the geodesics of such particles, but they arrived at the same result. So we show that the reducible mass is essentially the area of the event horizon. So they claim from a physical perspective, rather than a mathematical one, that the area of the event horizon cannot decrease in time. Actually, I came across this republication of Brandon Carter paper in 2020 as a golden oldie in the General Relativity and Gravitational Journal, in which I found written black on white that the irreducible mass can be used as the first demonstration, even before Hawking one, of the fact that the area of the event horizon cannot decrease in time. We should add some cosmological motivations for studying gravitational entropy, and they are based on the wild curvature hypothesis by Roger Penrose. And the wild curvature hypothesis conjectures that the wild tensor should be a good measure of gravitational entropy. And it is expected that the Big Bang singularity should come with a zero wild curvature, whereas big crunches and black hole singularities due to gravitational collapse should have a large wild curvature. In fact, you also know physically that during the collapse of a star, entropy is expected to increase by a very large factor. And since wild curvature quantifies tidal deformations, this is just the statement that we expect the black hole and the big crunch singularities to exhibit very messy and chaotic curvature behavior, perhaps like was in the ballistic lightning of Lipschitz description. So just a technical remark now. In differential geometry, and therefore in general relativity, we have the Riemann curvature, which is the full curvature of a space-time. Riemann curvature can be decomposed into a trace part, which is the wild curvature I mentioned in this slide, and a trace part, which is the Ricci curvature. Einstein equations only fix the Ricci curvature part. In Einstein equation, we fix a matter content of our space-time, and then we can compute the Ricci curvature. And so with physics, by physics I mean the Einstein field equations, can only fix part of a curvature, and the wild curvature is instead not fixed, is not determined by the Einstein equations. So we would like, in light of these considerations, to find a connection, a clear mathematical connection between wild curvature and gravitational entropy. However, implementing the wild curvature hypothesis is not a simple task. For example, we can try to follow the quite popular Clifton-Ellis-Tawakol proposal. First of all, it should be noticed that actually here we have the wild curvature, as in fact we want to implement the wild curvature hypothesis, but there is also the energy density and pressure of the matter field. And so this is not a measure of a pure gravitational field. It has been adopted by several authors for describing the formation of astrophysical structures like galaxies, filaments, voids over densities in late-time cosmology, both using exact and approximate formulas. However, as I discussed in the second part of my talk, thermodynamics of some non-solutions of Einstein equations is inconsistent with the value curvature hypothesis if we implement it by following these formulas. Then some authors have considered as an entropy density the square of a wild tensor. So we have tried to investigate whether the integral in the interior region of a black hole of this quantity, which is the square of a wild tensor, can reproduce the entropy area. And we find that the answer is yes, but only for Schwarzschild and Schwarzschild anti-de Sitter black holes, and not for Reiser-Nordstrom spacetime. And therefore, this formulas does not admit a general applicability in black hole physics. Some other authors, in the context of cosmological singularities, argued to adopt instead this gravitational entropy density. But you see, this quantity is essentially the wild tensor, but rescaled to the Ricci tensor. As I told you, the Ricci tensor is given by Einstein equations, and so it is directly sensitive to the matter content of the spacetime, and therefore is not a measure, this quantity is not a measure of a pure gravitational field. So let me now formulate in a sharp and precise manner the question we wanted to answer in our paper. In our paper, we looked for, and we wanted to find an appropriate quantity chi, which is function only on the wild curvature, and such that its integral in the interior region of a black hole provide the area. And we want this quantity to exist for all static and spherically symmetric, possibly distorted black holes in 4 and 5 dimensions. This is a spacetime metric that you can see, it depends on the function f of r, so we can have Schwarzschild, Reiser-Nordstrom, and other possible solutions. It also depends on this function h, which takes into account some possible distortions or some possible errors in the black hole solutions. These metric concepts have been adopted recently, indeed for constraining possible errors from gravitational waves dataset. So let me explain again where our requirements come from. We want our entropy density function to depend only on the wild curvature to be consistent both with the wild curvature hypothesis formulated by Roger Penrose and with the Bekenstein claim that the gravitational entropy is a measure of a pure gravitational field. And as I said, the gravitational entropy is non-zero even in vacuum, for example, for a sorted black hole. We want to integrate in the region inside the horizon, so in the volume of the black hole, again, because Bekenstein said that his notion of entropy is related to the amount of information hidden by the horizon. And then clearly, we want to reproduce the Hawking-Bekenstein area law, or in other words, as I mentioned, the Christodologue of finite mass, because this is a quantity which does not decrease in time. And we want our formalism to be general, so to work both for Schwarzschild and Reiser-Nordstrom, for example, again, because Bekenstein said that a good notion of gravitational entropy should not be directly sensitive to the matter content outside the black hole horizon. And as our answer is positive, so yes, we can find gravitational entropy density fulfilling all these requirements. We have applied the Newman-Penrose formalism. So we computed a quantity which is called psi2, which is a wild scalar. We computed its derivative again in the Newman-Penrose formalism. We integrate this quantity with respect to the spatial hypersurface volume element, and we integrate over the angles and up to the horizon, and we get the area of the horizon. So our formalism is fully based on the wild curvature, and so it is an appropriate result for a density of gravitational entropy. And we have not made any assumptions of the function f of r. So f of r is this metric function here and here. So our formalism comes with a general applicability to all black hole spacetimes, regardless of whether they are empty space solutions or not. So we can apply our formalism both for Schwarzschild and for research instruments. Our formalism can be applied also to Bardeen regular black holes in which there is no singularity. In fact, the crucial notion is not the notion of singularity, but actually the notion of horizon, up to which we have integrated here. So let's now make some physical considerations beyond this purely mathematical formalism. We think we have learned the following things about black hole entropy in general relativity. Black hole entropy is related to tidal effects because the whole curvature appears in the geodesic deviation equation, as we can read in this paper by Zacharias, in which a physical interpretation of the Newman-Peron's quantities have been given. Also, black hole entropy is a property of the focusing of light rays because we can use the Bianchi identity for the Newman-Peron's spin coefficient, which it turns out to be exactly our gravitational entropy density. In fact, already Bekenstein have explained that the change of area, the area variation for the horizon, which means the variation of entropy, is accounted for by this spin coefficient. However, it seems that no one have used this technique for clarifying or finding an appropriate notion of gravitational entropy density. So let's now provide a constructive algorithm for our result. So in theory, Whose Lagrangian comes in this form. So you see there is the Einstein-Hilbert piece in terms of rich scalar, and then we have a scalar field accounting for the matter content, when entropy is a surface integral over a section of horizon. This is not a trivial result. It may appear so, but it is not. And because it was found in a much more general class of theory, also with non-minimal coupling between curvature and matter field. It was found by Wald, who claimed that the black hole entropy is an Entropy charge, which is, as I said, just a particular case in general relativity. And so this is an integral, a surface integral, over the angle variables while the radial current is fixed. So in our formalism, we needed to write the normal to the surface, again using Newman-Penrose formalism. So we introduced the null thread obeying to this normalization, and then we needed to find an appropriate current, an appropriate density current chi, which integrated over the surface provide the area law. And it can be found very simply by just some algebraic technique. So using this normalization, we find the appropriate current, which is given by the sum of these two vectors. Then we apply Gauss theorem, and we find that the entropy is given by the volume integral of the divergence of L and mu vectors. And for black holes, these are exactly the Newman-Penrose spin coefficient. So we're adding some more motivation to the correctness of our result, which does not seem to be a merely numerical coincidence. We expect entropy to grow during the formation of a black hole, following the collapse of a star. And therefore, if our formalism is physically correct, it should deliver that entropy should not be maximized for a star configuration. And we explicitly checked this. So we went to the Tolman 1939 paper, and we took its solution, its Tolman metric form. The metric tensor is given in this form, and you see that the difference between a star configuration like this one and the black hole configuration I showed you previously is that the metric component GTT and the metric component GRR are now completely unrelated. And Tolman found an analytical solution for a function a and b, and the solution depends on three constants, y, x, and capital R. Capital R is the radius of a star in this model, and it was found such that the pressure is vanishing on R. So we computed the Newman-Penrose quantity psi2, and then we applied our formalism for computing gravitational entropy, starting from this mathematical formula, using this mathematical formula, but applied to the Thorman star configuration. And this integral can be computed analytically, and you see it is given by r squared, so by the area of the surface, minus a quantity which is for sure positive. And so we found that our formalism for a star configuration delivers that the entropy is not maximized. So consider that R is the boundary that gives the size of the star. We see that in a star configuration, according to our formalism, entropy is not maximized, and this is physically consistent with the fact that entropy should grow during the formation of a black hole result. And so, again, our result does not seem to be only a mathematical coincidence. So when one would like to understand the notion of gravitational entropy in cosmology, and this is what we are currently doing in these days. Let me now just explain what is the problem we have identified with the notion of gravitational entropy in cosmology. In a previous paper, we took this space-time metric, and you see that it depends on three free constants, A, B, and C. You can see that also it depends, it comes with either closed and open topologies, and you see there is a scale factor h. So this is a sort of inhomogeneous and anisotropic generalization of a Friedman metric. It is an exact solution if one chooses this mathematical form of the scale factor for these topologies of the Einstein's field equations of general relativity, where on the right-hand side, we have a perfect fluid whose equation of state related pressure and energy density in this form. So we have a sort of chameleon field, so the equations of state parameter depends on the background energy density, and it is a modification of the stiff equations of state. Because you see, we have P equal to rho plus a constant. And this constant C is called Bagge constant because it makes the pressure to be non-zero even when the energy density rho is at zero. And this metric has been studied mathematically by several authors independently many years ago. Since a stiff fluid is equivalent to a massless scalar field, this metric can be also relevant for describing the early universe, the primordial universe. And in particular, since it is inhomogeneous, it might be used for describing qualitatively and intuitively the formation of some exotic astrophysical structures in the early universe. So what we did is, first of all, we tried to put some physically meaningful constraint on the values of a free constant A, B, and C. So we have used two arguments, one from the cosmological holographic principle and one from the second law of thermodynamics. So the cosmological holographic principle tells us that the entropy of a matter field, so important is to always remember of which entropy we're talking about. So the entropy of a matter field inside the dynamical apparent horizon should be bounded above by the horizon aura itself in units of 4. So you see Hawking-Bekenstein is just this condition maximized. And so we find the location of the dynamical apparent horizon imposing this condition for the other radius. We solve the algebraic equation. Interestingly, we found that a dynamical apparent horizon in this space-time can exist if and only if the deceleration parameter is negative. Furthermore, we computed the horizon area very simply, and we computed the entropy of a matter field inside the horizon. You can see this is entropy of matter, and so it obeys the scale law as the volume of a system. We impose the cosmological holographic principle, and we get a constraint on the quantity C, on the bucket constant. We apply then the second law of thermodynamics to the entropy of a matter field. We require it to be increasing time. And by this mathematical law, we find that the second law of thermodynamics is now simply equivalent to the requirement that the size of the dynamical apparent horizon should increase in time. So we find some constraint on the constant A and B, but more interestingly, physically we find that in this spacetime, if the second law of thermodynamics holds, then the Weyl curvature is decreasing in time. So now let's compare the time evolution of the space-time shear of the Weyl curvature and of the derivative of the Clifton-Ellis-Tabacol gravitational entropy. So this is a formalism for computing gravitational entropy that I mentioned at the very beginning of my talk. So here I'm plotting the derivative. This means that since the derivative is positive all along the time evolution, it means gravitational entropy is increasing in time, physically meaning that possibly gravitational structures are formed. However, you see that the Weyl curvature is not monotonically increasing in time. So it is increasing and then decreasing. And in this formalism, the gravitational entropy is increasing thanks to the contribution of a space-time shear. And the values of the constant A, B, and C in these figures have been chosen to fulfill the two physical requirements I commented in my previous slide. And so the message behind this page is that you see gravitational entropy is increasing even though Weyl curvature is not. And so it seems that taking into account the Weyl conjecture of Roger Penrose, it seems that we need to deepen our understanding of the relation between gravitational entropy and Weyl curvature, which does not seem to be so trivial. So let me elaborate more on why we are interested in gravitational entropy, not only in black holes, but also in cosmology. Gravitational entropy is expected to increase when astrophysical structures form as a consequence of a gravitational collapse. So an astrophysical structure, which can either be a galaxy, a cluster, a filament, may form in one specific region of the universe rather than in another. And so the universe becomes inhomogeneous. And therefore, this is entropy should increase when astrophysical structures are forming, as by applying the interpretation of entropy as from statistical mechanics, as a notion of disorder and disgregation, because the universe is losing homogeneity. And when we look at the universe along a specific direction, we may or may not see an astrophysical structures, and it may have formed in one or in another spatial region. And therefore, spatial shear has increased as a consequence of structure formation. So the question that we are currently investigating is whether our notion of gravitational entropy, so the one we have introduced in our paper, is consistent with this physical requirement. So we want to understand, and we want now to show if that gravitational entropy in cosmology, as computed from the Weyl tensor following our recipe, is increasing if and only if shear increases. This might be true only for some specific content of a matter field in the universe, and we want to clarify for which one. And this would add quality to our proposal of computing gravitational. Let me now make some comments about black hole entropy beyond general relativity. Ours is a purely geometrical result because we have never used that the function f of r should arise as a solution of the Einstein field equations. So let me go back to remind you what f of r is. So what we did is we took this space-time metric tensor, and we never said that f of r should be Schwarzschild, should be Rest-Nostrum, or should be Schwarzschild anti-de Sitter black hole. And so we never enforced the Einstein field equations. We never enforced a specific gravitational theory. We simply completed it geometrically, and we showed that this quantity reproduces an other law on the horizon. Therefore, since this is a purely geometrical reasoning, if you change gravitational theory, if you find some exact solutions for a black hole in some modified gravitational theory, but you apply this reasoning, you will still reproduce another law.
Excuse me, you have 10 minutes.
Okay, yes, I'm
okay. 2:40. Thank you.
Okay. However, the problem is that in modified gravitational theories, the entropy does not obey any longer to another law, and this was claimed by some other authors. And so we know that in principle, a different combinations of curvature quantities should be adopted as a density of gravitational entropy. However, this seems to imply, and this comes with some very deep physical consequences. But we have shown that in general relativity, according to our proposal of gravitational entropy is a manifestation of some very specific physical effects, which are manifestation of tidal effects as related to the wild curvature and as a consequence of a focusing of light rays on the horizon, because I showed you that gravitational entropy can be computed as well from the Newman-Penrose spin coefficient. However, if in modified gravitational theories, if we are required to choose a different combinations of curvature quantities, then the physical interpretation of gravitational entropy changes necessarily. It necessarily changes. And therefore, the question is, what is gravitational entropy in modified theories of gravity? And while it seems a little bit clarified in general relativity, it seems that black hole entropy is instead very mysterious beyond general relativity. And this is all for my talk.
Okay. So we have 7 minutes for comments and questions. Thank you. Is there any question on Daniele's?
Yeah, I have a question.
Carlos, go ahead.
Yes. So thank you, Daniele, for this interesting talk. I would just if within your formalism of calculating entropy increases in astrophysical objects, is it possible to do it for non-analytic metrics? Meaning, have you tried some more complicated cases in which the metric is numerical?
So far, no. So far, no. But actually, your question makes me wonder if it is possible. And okay, so let's go back to what our basic invariants are. So I showed you two formalism. One is this one. And so for having gravitational entropy density, we need the wild tensor. And so wild tensor is derivatives of a metric tensor. And so perhaps if we can know it somehow, if we know it by some arguments, we can compute our gravitational entropy density even without having to reconstruct the full metric tensor. So this will be something bottom up. So in our approach, as I presented, it was top down. So starting from the metric, computing its derivatives, and so computing the wild tensor as its derivatives, as I showed you here. But perhaps if we know those derivatives for some reasons, we don't need to integrate back fully to the metric. And in the other formalism, the one by Clifton, Ellis, and Tavakol, so we need again to know the wild tensor. So it is enough to know the derivatives of a metric tensor, but not the full metric tensor analytically. And in that case, you also need to know the pressure and energy density. And so it seems possible, speculatively, at least speculatively, it seems possible, also in this case, to go to the bottom up, and so to compute, if we have these ingredients in our hands, we may succeed in computing the density of gravitational entropy without the need of having an analytical solution. However, I am unable to cite any paper right now in which this has been done explicitly.
I see. Thank you. Interesting.
Okay. Any other question for Daniele? We have one more. We have time for one more question, if any. Okay. Thank you again. Thanks, Daniele. Then we'll move to the next talk, which is Carlo himself. Are you?
Yes, thank you, Piero. I will try to share slides. A moment.
So the first talk by Carlo would be on the RAR model, and particularly on cosmological on large scales. Correct?
Yes. So, do you see my slides?
Yes. Yes. Great.
Okay.
Go ahead. Thank you.
Maybe I hope the transition to slides is okay. Thank you, Piero. Well, I will talk about this fermionic dark matter and the RAR model in an applications. This a bit an ambitious talk because I will have 2 sessions. I mean, two different blocks. So I will try to cover different applications of these theories of fermions plus gravity on galactic scales, cosmological scales, and also about the nature of the dark matter particles. So these works I will present has been done and are being done within a quite even larger and larger collaboration of people, including many different PhD students in CONICET and La Plata National University of Argentina, different master students there, and as well some postdocs and different researchers as well within Italy, Argentina, and as well France. As you can see, recently our collaborations with the University of Strasbourg and also with Pierre-Henri Chamani. So the results I will show are based in the last, let's say, 10-ish paper we have published in the recent years. And yes, and I will also present some news about our model regarding the galactic center and the EHT results. So let me go with the outline of the presentation. So I will first start from Blasso-Poisson to cell gravitating fermions as dark matter halos. Then I will talk about the thermodynamics of cell gravitating systems of fermions and how with this general study it can lead to a supermassive black hole formation mechanism. Then after this more theoretical introduction, I will move to applications to galactic scales. I will discuss how these models of fermions and gravity can be tested against rotation curve tracers. So we'll discuss the case of the Milky Way and as well as of other galaxy types from dwarf to clusters. Then I will also discuss application to galaxy scaling relations, the so-called radial acceleration relation, the dark matter surface density, etc. Then I will move to a short discussion about stellar stream tracers, which are very interestingly independent tracers of the gravitational acceleration field of the Milky Way, independently of the rotation curve. And as you probably know, the Gaia last data release has shown tens of these tens, maybe dozens of these stellar streams. So there are a lot of data here to analyze. I will show an example of the GD1 cold stream. And finally, I will dedicate a few slides about cosmological scales, either linear scales and evolution of perturbations in the case of these warm dark matter models, including as well as self-interactions, and then non-linear scales, recently applying also to the possibility to have n-body simulations within these cosmologies. Sorry.
It's black.
Yes, there was a problem with the. Now you see again.
Okay.
Yeah. Okay, so let's start with a brief introduction about and motivation about the dark matter I will speak in this talk. So here we have a picture of the chronology of the matter energy evolution in the universe, and then the main task of this talk will be to deal with a given dark matter candidate, which is present at a bit after the inflationary epoch, and will decouple in a given regime, and will start to evolve first in the linear regime, the dark ages, and then in the non-linear regime, forming the seeds of the galaxies we see today. So the challenge will be to try to understand and link the microphysics of these dark matter fermions with the morphology, the latent morphology and distribution of dark matter in galaxies and stability. So let's start with the success of the lambda dark matter paradigm. So this paradigm tells us that astrophysical observations, including the CMB, the BAO, Lyman alpha forest, and the local distribution of galaxies, ranging from horizon scales to typical scale between galaxies, are all consistent with a scale invariant primordial spectrum, dominated, as you know, roughly of 70% of energy, 20% of matter, and roughly 5% of baryons plus radiation. So one of the, let's say, the main compelling evidence for the system of non-baryonic matter comes from the CMB, as you probably know. So a picture of the right is showing you a picture of the CMB, this temperature distribution, which describes how primordial density perturbation grows into galactic structure, and then when matter falls into this potential well, they finally represent a temperature spectrum, which is directly related with the matter power spectrum, in such a way that if we do not include dark matter at all, or we decrease the amount of dark matter, is the relation between the second and third peaks of the power spectrum are very sensitive to this variation. Therefore, as you can see here in the lower panel, when you put less dark matter in your lambda CDM cosmology, you have the heights and the position of the second and third peaks changes without and then for not fulfilling with the data, and the same happens if you, for example, want to put more dark matter. So besides the CMB compelling evidence for the existence of dark matter, we have also a real, measurements of the dark matter distribution in the local universe, as you can see here in the plot of the left, which shows this structure, which is the so-called cosmic web. So it's not totally homogeneous. It has filaments, voids, and nodes. And for example, if we would like to make a zoom of one of these nodes, let's say at 100 of kiloparsec scales, at the upper picture of the right, we see how matter and dark matter in this case distributes on these large galaxy scales with substructure inside, following the bottom-up hierarchy of structure formation. This is an example from a simulation. And in the picture at the bottom, you can see how this matter distribution reflects in the circular velocity rotation curve, which shows that the baryonic component we separate here cannot follows a Keplerian trend towards the outer part of the galaxy, while the observations show more or less a constant trend in the halo region, therefore telling us that there is a missing matter component which one needs to understand. So we will try to attack this problem with a fermionic candidate, and therefore let's move to the attacking the problem of dark matter halo formation from a collisionless relaxation considerations. So we start with the Blasov-Poisson equation, which is the equation you see on the left, which has the phase space distribution function, which is a function on space, velocity, and time. And so the challenge is to try to solve this equation, try to find a most likely phase space density when the system goes to relaxation. And there are two standard ways to do this nowadays. One of the main avenues to attack this problem is through embodied simulations, as you probably know. And but in this case, we will start attacking this problem through a more statistical and thermodynamic approach, in which we first decompose this phase space distribution into a coarse-grained averaged term, F bar, plus F tilde, which are fluctuations, fine-grained fluctuations. By plugging this decomposition in the Blasov-Poisson equation on the left, we have a new equation which resembles the Blasov-Poisson in the left-hand side for the coarse-grained phase space density, while in the right-hand side we have a diffusion current, a derivative of the diffusion current with respect to velocity. So it is telling us about the diffusion convection, the typical equation of a kinetic equation, in this case coupled with gravity. Therefore, these equations have a very nice form, but are very complicated because we don't handle how all the microphysics on the fine-grained fluctuations. So a way to be able to obtain a most likely coarse-grained phase space density is to impose a maximum entropy production principle, so that the coarse-grained entropy is larger or equal 0, the derivative in time. And therefore, by this method, it is possible to obtain a most likely coarse-grained phase space density at relaxation. So stationary, now these F bar do not depend on time, and which is of the form of a Fermi-Dirac type, resembling or probably recalling you the Lindenbell treatment of violent relaxation in the 70s, which indeed this maximum entropy production, what has done is extended extending this or generalizing this Lindenbell distribution function by accounting for escape of particles, what you can recognize with the term in the numerator of this, the factor in the numerator of this distribution function, for which for energies larger than given energy, the system is depleted and have no more particles inside. So then this treatment can be applied for fermions. It has been shown that can be, because Lindenbell first applied to stars, thinking that, for example, when globular clusters or other larger galaxies virialize, they can have an increase in density towards the center due to this binary relaxation. But then Poole and others show that it can be also applied for indistinguishable particles, this thermodynamic approach, so for fermions. And in this case, for example, fermions, and in this case, you have in the case of fermions, the maximum accessible value of the distribution function is given by the Pauli principle. So now we have a formal and self-consistent way to provide a corresponding phase density, meaning how the particles are moving in phase space when the system has reached to an equilibrium. We will now face the challenge to build an equation of state for this system. So we first follow the prescription that fermions under zero gravity follow a perfect fluid approximation. Therefore, it allows us to solve the Thorman-Oppenheimer-Volkoff equations of hydrostatic equilibrium because they are working under this perfect fluid, and we will do in spherical symmetry. Therefore, the most general equation of a state in terms of this fermionic phase space distribution function has the form that you can see here. So this F is precisely the coarse-grained distribution function I showed in the slide before, coming out of violent relaxation mechanisms. And this theory has 4 free parameters: the particle mass, the dimensionless temperature of the gas, beta, the dimensionless degeneracy parameter, theta, and the cutoff parameter related. The only 2 relevant equations are the above 2 equations in the panel of the right. So the mass equation and the TOV equation are coupled with Klein, Tolman, and energy conservation, which are the last 3 equations. And therefore, the challenge now, once we have this coupled system of highly nonlinear ordinary differential equations, is to solve the boundary condition problem, which has for regular solutions at the center, and for the most general case of positive central degeneracies, theta 0 larger than 0. This is a reminder that if one would like to solve this equation for negative central degeneracies, one can do, and the solution will become Boltzmannian, because the Fermi-Dirac phase space distribution will look as a Boltzmannian phase space distribution with a cutoff in energy, and therefore we will reobtain the traditional result of King profiles for fermions. So the most general solution after this approach has a profile which looks as the picture I'm showing in this slide, in which it has very interesting behavior because it covers both regimes. So the outer part, the halo is maintained against the gravity with thermal pressure, while it continuously increasing density and in degeneracy towards the center, and this central core is maintained against gravity through degeneracy pressure. So both regimes are continuously inside the solution, and this solution has been solved for given boundary conditions in the outer part, typical for spiral galaxies of 10 to 11 solar masses. And therefore, that is why you can see quite good agreement with other typical profiles in the literature in the halo region. But maybe the interesting thing to see here is that this is a logarithmic plot. That's why this central feature is seen so so clear, and that the industrial and methodic profile, which are fits coming from n-body simulations, they are only possible until, let's say, kiloparsec scales, than which they are only extrapolations due to the finite resolution of the simulation, while our semi-analytical approach allows us to see very inside the matter distribution, and therefore to try to grasp if the quantum pressure of these dark matter particles are really having an effect inside. Therefore, this central core fulfills the quantum condition, so the Broglie wavelength is larger than the interparticle mean distance, and so all these cores are so-called quantum cores, and this dark matter profile depends on the particle mass. We will now, before moving to the applications, move to another very interesting theoretical analysis, which is trying to solve the thermodynamics of this cell gravitating system of fermions, and what we can learn about the stability, because these solutions that I have shown here are equilibrium solutions of the Einstein equations. But an open and interesting question that we have now attacked is if these solutions are stable against cosmological timescales, and if they can form at all in a given cosmological framework. Therefore, how the gravitating system reaches the steady state is not an easy task. Therefore, having a phase space distribution solution, so that's the one for Fermi type, does not necessarily imply that the solution is thermodynamically stable. In order to find dynamically and thermodynamically stable configurations in general relativity, we need to find solutions that maximize the global entropy, meaning the entropy, which is the capital S, is the entropy integrating the Gibbs-Duhem entropy density, which accounts for the pressure and density terms, as well as the chemical potential. So the stability problems, once we have an expression of the global entropy, that in this case we have, because as I've shown here, we have the specific expression of pressure and density and particle number density and temperature, because we have it from the equations that we have solved before. But finding the stability will imply to find second order variations, the variation of second order in this entropy. And this task in general relativity for barotropic equation of states is a very hard problem, has not been solved up to now. The only solution is GRR for barotropic equation of states. But it's very important that we have another criterion to still analyze the stability, which is the Katz criterion. It relies on the derivatives of the caloric curve, so energy versus the inverse of temperature of the system. And therefore, we can analyze the series of equilibrium, all the possible families of equilibrium along a caloric curve for fixed total particle number. And we will do, for the first time, this stability solution has been applied for, not for toy models of given mass, but for large system of masses of order 10 to 10 solar masses. This is a very hard numerical problem, because it implies to solve this coupled system of equations hundreds of thousands of times with very large numerical precision, and then for this caloric curve that I'm showing here in the picture of the right, that that covers in continuous blue, we have all the stable solutions. So the ones that are either global or local maximum of corresponding entropy, and in dashed, which is when this small spiral on the top right is starting to appear, when the spiral, so the system goes like this. So when in this zoom, in solution one, solutions are in a diluted regime, so degeneracy is in this case negative, because in this case we cover all possible degeneracy. So for negative, so start diluted, and these solutions are global entropy maxima. Then this caloric curve starts to develop a spiral, but then interestingly, this spiral does not go to a singular isothermal sphere, but derolls due to the Pauli principle. So interestingly, the quantum effects come to halt the gravothermal catastrophe, typical of Boltzmannian distribution function. But remember, we are working here with a fermionic distribution function. And so when derolls, we pass through solution 2 and 3, and after point B, there is a second stable branch of solutions, which, as I will show now in the next slide, will show this core halo behavior, but are stable. And then if we continue in this caloric curve, we reach at some point the degeneracy is so large that reach the last stable configuration, is point C, because at a given energy, there is no accessible state of energy. So in the x-axis, we have a normalized energy, so mc squared normalized. And therefore, there are no accessible state, and the system will collapse. And then this branch dot line to the second spiral is a typical behavior of already collapsed solutions in general relativity. So therefore, in order to try to apply this approach in a cosmological framework, because the one would like to do is to these 10 to the 10 solar masses is not put in by hand, as obtaining at a given redshift, starting from a quantum matter cosmology with this 10 keV particle mass. So the challenge is to first calculate the power spectrum with this particle that decouples relativistically from primordial plasma, then apply a pressure sector formalism, because we are not doing an embodied simulation, so we apply this pressure sector formalism to obtain the virial mass at a given redshift in cosmology. So we use this top hat function W, because these particles are cold enough, and we use the critical when the mass variance reach the critical over density, typical of spherical collapse models, we can obtain this virial mass. And therefore, this is a picture showing the virial mass as a function of the mass scale, the virial radius as a function of the mass scale, and for different cosmologies. So we have done, in the red, we have done for 10 keV. Let's stay for a moment in this example, and pink in 48 keV. So let's stay in this world normative cosmology. But as you see, for the halo masses, already above, let's say 10 to 9 solar masses, the cosmologies become the same with respect to warm, respect to cold. And so we choose, for example, this point here of this green triangle. And this is a virial mass of 510 to 10 solar masses, which happens to be start to form at redshift 10 in the cosmological. This C virial is order 10 here. And therefore, once we have this boundary condition but obtained from a cosmological analysis, we will use now this stability criterion to analyze all the possible families of solution for this virial mass. So for this specific particle mass, we have these 3 solutions, because this particle mass, I will go back a moment in this slide, correspond to this energy, fixed total energy, or so with this given total mass. So these caloric curves, once you have you do in the microcanonical ensemble, so you fix the total energy, you have all the solutions that intersect this given energy with the caloric curve. So our solution 1, 2, 3, and then we will have a solution 4, but it's in the non-stable regime. So we have these 3 solutions. Interestingly, we have the blue solution 1 is an stable solution, which is of king-like behavior, which can be stable and astrophysical interest. But also we have this new solution, which is solution 3. 2 is unstable. It's very similar to 3, but it's unstable because it's a saddle point of entropy. But solution 3 is stable, and is of core halo behavior, which we will see now that is also of astrophysical interest when applying to galactic observables. this has been done for ICRANet and has been published. This work has caught quite attention in the literature. It was an international press release by the Royal Astronomical Society and went to different media, because as I will show now, this approach of self-gravitating fermion in thermodynamics can lead to the concept of supermassive black hole formation. Because as you can, for example, you can maybe foresee already these solutions, like solution 3, this core can be compact enough in order to become critical. Therefore, this we can analyze not only from the thermodynamic criterion I showed, the caloric, but also from the turning point criterion, which is studying all the stable solution along this plot, which is central density versus core mass. So we can see here that to the left of this plot of this maximum, all the solutions are stable, because are these between the branch B and C that I show in the caloric curve. But to the right of this plot, the solutions are unstable, and therefore they are in agreement with the turning point criterion theorems, for example, that you can find in wall papers, saying that in a turning point criterion, all solutions to the right necessarily have to be unstable, while solutions to the left, there is no unnecessary condition, and they can either be stable or unstable, which in this case we demonstrate that are stable solutions. For the core mass, then you can see in the paper what happens for the total mass. But interestingly, you can pay attention to this value, specific value of the core mass, this quantum core at the center of the distribution, which is of the order of 10 to 8 solar masses for this particle mass. So at this maximum, the core mass is of the order of the Oppenheimer-Volkoff mass, and so after point C it is overcome, and so for the degeneracy pressure of this quantum core, which were stable prior to this point, cannot support its own weight no longer and collapse towards a supermassive black hole. What you see here in this case is for 10 to 8 solar masses, while the halo part still lives, because it is a huge system. Only the very central part is what collapsed. The release of energy there is negligible respect to the total energy of the system, and therefore we can have also a supermassive black hole out of dark matter in the early universe with a surrounding halo of fermions there. So this is interesting because it may provide initial seeds for formation of observed supermassive black hole in active galaxies without the need to start with population 3 stars and then by subsequent accretion, but now with this larger thing, because the key point here is that galaxies, the dark matter halos in galaxies in the high-resolution universe, the key concept here is that can born in this core halo state, and therefore this is a completely different way of seeing dark matter halo formation, because what we have learned until now from embodied simulation is that they have this more or less NFW behavior in ASTO in the outer part, but we don't have access to what happened in the central regions. There are extrapolations, we don't know what happens, so we have to put a singularity there in the center. But this is a continuous solution which may bring interesting avenues to study the supermassive black formation and coexisting with halos. Okay, so in my last part of the talk, I will move to galactic scales and rotation curve tracers. Let's move fast to the Milky Way observables. So here we have the rotation curve of the Milky Way. And let's add the S-star cluster, as well velocity of the stars in the very central region, milliparsec region of the galaxy. And let's wonder if this core halo solutions can answer for this grand rotation curve, including the central S-stars, without introducing the singularity at the center. So we find a family of solutions which are of the form we showed before, but now specifically for the rotation curve data of the Milky Way, as you see here in the picture of the right, which so the dark matter behavior of these fermions can answer for these observations, but increases with this quantum core towards the center, such that they also fulfill with the average circular velocity of these best resolved S stars. And it can be done for solutions, which goes for a particle mass of roughly 50 keV, because there is an inverse of proportionality trend. So the larger the particle mass, the more compact the central core for given halo boundary conditions. And so therefore we can reach the most compact solution in continuous black, which has a mass of 345 keV, which is the critical prior to collapse. So interestingly, this is numerically is not an easy task, because one has to solve. In this case, has been shown with shooting methods for different boundary conditions until the distribution matches the rotation curve. But it can be done much more precisely with machine learning techniques. This has been done recently by one of my PhD students that we present now in next month, University of Chicago, about the deep learning techniques used to fit any rotation curve. This is an example for this. The important thing of this tool is you can put vary many parameters, 10-ish of parameters. For example, if you, independently of the Milky Way, if you want to take some baryonic distributions of a given galaxy, and you have the mass models, for example, for bulge, disk, and gas, you have some mass models, you put to vary these three parameters on top of the three parameters of the dark matter distribution. Of course, if you have an analytic solution for dark matter, like NFW, is easier. But in this case, which are numerical solutions, is much more complicated. But therefore, these machine learning techniques allow us the possibility to minimize a loss function, which is the picture you see on the left. This loss function is no other than a weighted least squares when all the differences with respect to the prediction of the model and data are covered, and it can be minimized in a few hours time. While, for example, if you would like to attack this problem with a Monte Carlo technique, it will take days or weeks in a normal computer. But now let's go into the last part of the talk. Let's move to the at least of the first part, to the geodesics of the stars, because up to now what we have done here, here are the average circular velocity of the S stars, because this is a circular velocity plot. But as you know, the S stars are ellipses with the very supermassive compact object at the focus, and therefore, if one would like to answer for these geodesics, one have to use all the most up-to-date data taken by all these telescopes, and one would like to as well demonstrate the relativistic redshift that has been observed for the S2 star, as well as the precession, and also to the other dust-enshrouded object, G stars. And therefore, recently we have, with the nice work collaboration with Eduard Becerra, that awarded, probably if you were yesterday, I showed that these results awarded this year the ICTP Cipher Prize of honorable mention of classical gravity and applications, in which we have shown that in this rare model of self-gravitating fermions, the central core can answer for the dynamics and the astrometry of this star in the plane of the sky, with very similar precision that the black hole paradigm you can see here. And in this slide, I show now the line of sight radial velocity, or sometimes called Z, redshift of the star, that you can see here in the left upper plot, when the star is approaching us and then receding us with this typical cyclic plot. And interestingly, it can be shown that the redshift excess, meaning when the galaxies, when the star goes fly by towards the pericenter, it shows a relativistic effect due to the relativistic redshift, which in this peak implies that this is Z minus Z Keplerian. Keplerian is the one if Newtonian, if Newton gravity will only apply. But then we see that there is a difference in this nearby pericenter around 2019, this S2 star, which demonstrate that interestingly, at 1,000 Schwarzschild radii of distance of this S2 star pericenter, already we can see general relativistic effects in its orbit, either in a singularity paradigm or in a very compact dark matter core. Then this will not speak much about the precession. We have also recently calculated the precession of the S2 star in terms of this quantum dark matter core. This will be the topic of Valentina talk. She will speak in the late afternoon today, when we can see, but I will just roughly comment that the fact that the dark matter core is an extended mass, so we are not in vacuum, we are in an extended mass distribution. Therefore, they're interesting combined effects. So the central core will allow for a prograde precession, while the extended mass, which is the atmosphere of this dark matter core, will cover and fool the orbit of the star, causing a retrograde effect. And so we will see later that depending on the particle mass, this periapsis precession can be negative or positive. But interestingly, up to date with the actual precision achieved by the campaigns either in North America and Germany of this star data cannot disentangle between the two theories. And we will have to wait to 2026, roughly, which is the next apocenter passage, where actual precision measurement would disentangle both behaviors, or if we see, for example, a hint of retrograde precession for the S2 star, that will be a hint for the dark matter distribution surrounding the Sagittarius A star, and if not, it will imply that this dark matter contribution surrounding is so that only the dark matter core will be the mainly causing of this precession. And then
they're getting close to the 40 minutes, Carlos.
Yes, thank you, Piero.
But you have the other talk, so we can juggle.
Yes, I will. These are my last two slides of this first part, and this is just to mention that we have also this other very nice work in collaboration with Eduardo Becerra and this PhD defended last year. He showed that not only for S2 we can include the 17 best results S stars, and to show that this it has to do with any fine tuning. It's just is really the metric of this dark matter space-time can answer for the dynamics of all these 17 stars with similar precision to the black hole. Therefore, a very question that you may be wondering right now is we have seen recently the EHT image of the so-called black hole at the center of our galaxy. And interestingly, an important question is how this dark matter model stands with respect to these recent EHT results. So this is a picture of the paper of the EHT collaboration, where show this bright, thick ring of light, which has a diameter of 50 microarc seconds, so roughly 10 angular gravitational radii. Remember that a gravitational radius is gm over c squared. And therefore, an important question is, does exist any fermion core compact enough of this dark matter distribution which can cause or develop a similar image than the black hole? Well, interestingly, we are now attacking this problem since the last year with a big collaboration with people expert on ray tracing algorithms. And this has been done with general relativistic ray tracing code named Skylight, which has been recently published in this paper. And therefore, what we are doing is putting a surrounding accretion disk where light is coming towards this central dark matter core, and we are seeing that, interestingly enough, not yet collapsed dark matter cores can develop similar image and showing these strong lensing effects around the central object and casting a shadow as well. This is important. And just the last slide is to show that yes, these are two pictures already with a Gaussian filter, but we can put in our simulation to show the blurred image caused by this light ray coming from an accretion disk. In our case, it's just a circulation EIM to start with, and seen by a verified observer in the place of the sun. And the upper plot is an almost edge on view, while the plot of the bottom is almost face on view. So you can see that already for this not yet singular, highly compact dark matter cores, you have a shadow feature. And therefore, it is very important to proceed, continue with this investigation for more realistic accretion disk theories in order to contrast with the EHT data. Thank you, and I am open for questions in this last part.
Thank you, Carlos. Fantastic results. Congratulations on all this. I mean, applying this method from black holes to to large-scale structure. I think it's quite a challenge. Are there questions? I do have one, but please go ahead with the audience with questions if you have. Okay, so I'll going back to the distribution of cluster-like structures. I mean, structures on the cluster scale that the RAR model might have an impact on. Would you have a plot comparing in the inner core the expected profile from the from the standard LCDM simulations, which we all know, with your model in the inner core of clusters?
Yes, thank you. This I will present in the second part of my talk.
Okay. Well, okay.
Yes, because up to here was the theoretical results plus application to galaxy scale, so the Milky Way. But in the second part, I will move to other galaxy types, including large elliptic galaxies and cluster.
Okay.
Yes. So, but yes, I can show in a moment this, Piero. Okay. But so maybe yes, and maybe with the plot will be better.
Right. And you know, one of the, probably you'll talk about this too in the second, but just in case, then you can touch on this in the second talk. But you know, one of the issue there is the back reaction effects on the baryons, right? Because clearly, dynamically, the dark matter interacts in a way with the baryons. And so, is there any difference with your model in the back reaction effects with the baryons compared to standard LCDM, or? Yes,
this is a very important question, Piero, of course. And we have now, we have attacked somehow this problem, but in this following manner. We took recently the data set of Spark, the Spitzer catalog of the Spark Galaxy data set, and tried to make a statistical analysis with our model respect to, for example, models of purely CDM, so NFW, but also generalized NFW files accounting for baryonic feedback to show that which model can do better, meaning, because this is an interesting point. So we have shown, this paper will be appear in APJ next month, probably, it's under review, and we have a positive first referee review, which is, let's say, so baryonic feedback has to be there, but it's not sure up till now up to which extent we have to put all the weight to baryonic feedback to solve the tension of lambda cold dark matter. What we have shown is that from this maximum entropy production principle treatment for fermions, our profiles can fit similarly well this Spitzer catalog respect to the generalized NFW accounting for feedback. So we are wondering if there are more physics to be considered rather than only baryonic feedback in order to solve this problem. But but in order to fully to account for any feedback, we will have to include also in our simulation the baryons, which up to now we are treating as independent components. But yes, this is the answer I can give you up to now.
Okay, thank you.
Okay.
So if there are no other questions, you can move on to the, there's Jorge.
Yes, thank you, Piero, and thank you, Carlos. I just I would like to ask Carlos, what are the main difference that you expect in treating bosons instead of fermions using this kind of approach?
Well, this is another very interesting question. Meaning, if my answer will be more mainly on the literature that has been put trying to cover the problem of having a boson star as an alternative to the black hole in the center of the Milky Way. We have not attacked this problem yet, but the results up to now are that well, a boson star can be, of course, it is again horizonless solution, very compact, cast as well shadows. It has been shown in simulation recently with another ray tracing code a few years ago, that they also have this pattern of light. But what I cannot fully say, Jorge, is regarding the intensity of light, the specific pattern respect to the EHT, because the last results I have seen were shown a few years prior to the EHT results. But the important point is that this horizonless compact object of boson star can as well cast shadows. The only difference, a big and important difference with respect to our model, is that with bosons, you have only this boson star there, which is not, and this is important because our model continuously goes to the halo, so can explain both regimes. In bosons, you have only the boson star at the center. You cannot have this extended distribution outwards, and also it's not clear where this very light particle mass of this boson come from cosmologically. While this is more challenging to explain the cosmology of this particle in this boson star respect to this warm dark matter candidate. But as far as I can tell up to now, Jorge.
Well, unless you have a transition from a condensation in the center and an ordinary boson in the halo.
Yes, this is interesting. Until now, up to now, it has not been shown a continuous distribution of bosons having both the central and the outer. It's true. What you are saying is that you may have the condensate at the center, while in the outer part, your bosons could be, the temperature could be below critical and therefore be in a dilute state.
Yes, that's right.
Yes, I think this phenomenology is interesting. It's open way to deal with for both. But I think it's not impossible. But I didn't see any work yet on this. But I think it's probably maybe possible. I'm not sure, but maybe so. Yes. Yes.
Okay, so you can move if you want to the next talk.
Yes. So, okay, I will, let's this after the first part, I will go to different galaxy types and galaxy relations. So, of course, one important question in this model is if for the same particle mass, one can have different families of solutions of these dark matter halos, which are in agreement with different scales from dwarfs, for example, small dwarf of 10 to 7 solar masses, from for example, that we can have here in the Milky Way satellite, then larger spirals of 10 to 12 instead of our galaxy, which is somewhat smaller, and larger ellipticals. Therefore, we have done this work taking data from 8 best resolved stars from those galaxies on the Milky Way. So with this typical 10 to 7 at 400 parsec, and spiral elliptical of this value, you can see that the green dots in the upper panel correspond to these halo constraints. Which are fixed, right? We solve this system of equation for these specific halo boundary conditions, and we wonder which are all the possible free parameter space of these fermions which are in agreement with this boundary condition. So we have these families of solutions depicted in light blue, shaded blue here. But please pay attention. This is, I think, very interesting. That, for example, in dwarf galaxies, you can see that the core, if you see my arrow, corresponds to the point where my arrow is. So it goes from order 10 to 3 up to 10 to 6 solar mass for the core. So it means that in this paradigm of dark matter, dwarf galaxies can born with this core halo in which the core already has the mass of typical intermediate, so-called intermediate mass black holes, because typically covers masses from 10 to 3 to 10 to 6. And very interestingly, this, you may wonder, oh, but what 10 to 6 respect to the 10 to 7 is very large proportion of the core mass respect to the halo mass. But interestingly, there are different, few galaxies, but there are galaxies which has been shown that the dark matter, the so-called intermediate mass black hole, is comparably mass with the total halo of the galaxy. This is incredible, but there are some cases of this in the literature. And interestingly, our model can go in that direction as well. Well, and then here is the question of Piero. Unfortunately, I put here only up to the plot of ellipticals, Piero, but if you see this paper, this reference of 2019, you will see that the density profile of the galaxy cluster, which in our case we study a 7 well-resolved bright cluster of galaxies of order 10 to 15 solar masses, yes, or 10 to 14 maybe, and the behavior is very similar to this one of the large elliptical. So, meaning that the cores, that the rising of the core, which will have a consequent rising in dispersion velocity towards the center, starts already in the case of bright clusters at a fraction of kiloparsec. This is interesting. In the case of this elliptical, you can see start already at order 10-ish so 1% of kiloparsec. But in the case of a cluster of galaxies, already at a small fraction of a fraction of kiloparsec, the dispersion velocity start to rise. So this may be interesting to compare with data of clusters towards the central region, where I know there are interesting strong lensing behaviors. Okay, so let's move to line of sight dispersion velocity. So, because up to now I have shown the families of density profiles, but now let's compare with the data, because for example, in fornax of Sculptor dwarf galaxies, we have quite a lot of data spanning from tens of parsec until thousands of parsec. And therefore, it is interesting that, for example, our model can do very well, similarly as the best analytic Kort-Hernquist profile working for these galaxies. And so this is interesting that solving the Schinn's equation, and you know the Schinn's equation, because these are not these galaxies, so they are more in spheroidal dwarfs. So you have to apply the Schinn's equation. You have the line of sight dispersion velocity of data, and then you have the surface brightness of these galaxies that you can have put as an input, the mass to light ratios of the stars, and then you have your distribution of dark matter. With all of that, you can solve the anisotropic Schinn's equation, and you can find these interesting fits. This is a work in progress. We are about to submit soon. And this is the case of, in the picture of the right, of a spiral galaxy, where we can see that it can provide quite good fits. But let me go to the work I was telling a few minutes ago about the SPARC data set. So this is a large set taken by the Spitzer catalog of around 175 these galaxies, out of which we selected, due to different inclination angles and other bad data, we end up with 107 these galaxies. And we made this study to see, because there is a diversity in profiles in these galaxies, because probably, for example, let's compare two extremes. In the picture of the right, you see this wavy behavior of the data in black, while in the picture of the left, this is a much more continuous trend of the rotation curve, developing a nice maximum. So these are two typical opposite regime, which in this case, probably there is not totally known what is the underlying reason of this wavy behavior, but it's probably known due to tidal interaction with other galaxies, or yes, which has been maybe underwent some merger, or the outer part is not totally in equilibrium. So there are different possibilities for this. While this is a more steady case in the picture of the left. And what I show here is different fits for three different models. In yellow is the generalized NFW, which is the one which accounts for baryonic feedback. We can do much better. I didn't put here the statistics, but the model that best works for this are the INASTO profile, or also the generalized NFW, which accounts for baryonic feedback, while our model can do comparably well with this generalized NFW, while much better both than the typical CDM NFW profile. So this is an important point, because we discussed this point that, interestingly, it is not clear how much weight one have to put to baryonic feedback. Of course, baryonic feedback has to be there, but it's not clear, because this is already an open question, and it's a bit fine-tuning sometimes, depending on the communities, how to deal with baryonic feedback, depending on the size of the galaxy. So we are here addressing this issue as well within our maximum entropy production formation of galaxies. This is I want to show here. Here I put, yes, the statistics. I thought I didn't put, but this is the picture of the left, the cumulative distribution function. So the way to interpret this plot is that, for example, let's say if we stop at 0.5, so let's say that half of the galaxies have of the galaxies in the models of this, let's say, fermionic model and INASTO, for example, do much better because have a much less reduced chi-square respect to NFW. Or vice versa. So for a given chi-square, let's say 1, we have much less galaxies in NFW achieving this chi-square than the other models. So the other models can do much better overall with this SPARC dataset. And in the picture of the right, I show this. I think is very interesting because this is a first linkage with typical halo tails of profiles coming from embodied simulation. So I have shown you before the coarse-grained phase space density of fermionic type, but you can wonder, well, which is specific morphology of the halo tail of these models, because you have seen that that is have a cutoff and therefore is self-bounded. But therefore, interestingly, with this diversity of halos in the spark data, we can go from the most compact halo, which is of polytropic type, with an polytropic index of n like 5.5, which is the dot dashed. But we can also have very good fits for this WP is a control parameter of our theory, the cutoff parameter, which can reach to the so-called Barker, very similar to Barker, because you can see that, for example, this WP order 7, the polytropic tail start to become power law, all down to more or less the virial radius. So this is very important because it means that our model can provide halo tails with power law 1 of r to the -3 towards the outer part, like Barker profile, and being cored at the center. Then we have attacked the problem of, okay, this is okay for given rotation curves of individual galaxies, but what about universal relation that covers, in average, many different galaxies? So one of these last relation is so-called the radial acceleration relation and the baryonic Tully-Fisher relation, which are important relations that any dark matter model should fulfill. And so the radial acceleration relation is a non-linear correlation, as you see here in the plot, between the radial acceleration caused by total matter, so in the y-axis, respect to the one generated by baryons only in the y-axis. The way they disentangle baryons from total is because they have the light observed from stars, the sulfur brightness, and therefore they can obtain mass models for the distribution of light, and then they have independently the rotation curve tracers of H1 and H2 regions of the galaxies, and therefore they have this interesting correlation. Any pixel here are many measurements of radial acceleration at a given radii, but for many different galaxies, because this is a universal relation. So it is in the part where the correlation deviates from linear, it implies that it's more dominated by dark matter, so in the outer part of the galaxy, while towards the matching with the linear trend, it means that the baryons start to dominate, and therefore it's very difficult. The matter is start to be comparable, sorry, or negligible. This is in the inner halo parts, not in the core that I showed before, because this observation cannot reach until let's say kiloparsec scales at most. But therefore, here I have shown that we have shown in this paper that will soon appear that the fermionic model can reproduce very well this radial acceleration relation respect to the best model up to now, which is the DC14, which is this generalized NFW accounting for baryonic feedback. Important to say that this acceleration relation do not imply the need. I mean, because there have been claims that this A naught here parameter, which is a best fit parameter in this correlation, arise naturally in Mond theories of gravity. But there have mounting evidence yet that many different paradigms of colder matter, accounting for baryonic feedback, or our fermionic model from maximum entropy production, can as well reproduce very well this correlation. And then you don't need to go to these Mond theories. Okay, I will now move to another. This is interesting because you can attack the problem of testing the gravitational potential of galaxies and the acceleration field with independent tracers than the rotation curves. For example, stellar streams. Stellar streams are key tracers of the gravitational potential, and in this picture I shown an update of 4-ish stellar stream comprising the D3 Gaia data release. with the data of roughly 10,000 of stars, which have been analyzed in order to disentangle these very nice streams that are all the way in the above and below the galactic plane. And I will go fast because Martin Mestre will show very detailed the application of our model to stellar stream, but this is just to mention that we can take, for example, the cold stream, which has been very much analyzed in the literature, the so-called GD1, which is a unsteered and tidal disrupted globular cluster, which shows this steered behavior in the sky due to these tidal effects caused by the host, meaning our halo. And therefore, it shows that have different patterns. The stream, some spurs, but it's clear that it is a very narrow and trend in the angular position of the sky. So the challenge is to take the observables of this stream, which are the angular position along the stream in these specific coordinates, the velocity, heliocentric velocity, the proper motions, mu alpha, mu beta, which are data from Gaia, and the photometric distance. So we have therefore Martin will show in detail. It's very interesting fact that our profile can answer very well, can fit very well all this data of the stellar stream. And one interesting result that he will show is that fitting our best parameter, we find a good fit similarly or even a bit better than the best fit from the literature up to now, which was from a slightly oblate NFW profile, which was needed to apply in order to fit this data. But now we show that with spherical symmetry and with this model of fermions, you can fit similarly well the data. And finally, I will move, and I think I will try to go now faster with cosmological scales. Up to now, I have discussed the role of these fermions that once decouple from the primordial plasma in, let's say, in a relativistic regime, then transition towards the non-relativistic regime until semi-gravity entered into play, starting to seed put the first seeds of halos in the chronology of the universe. But now it's interesting of precisely how you can solve the power spectrum in these key big cosmologies, and then all the way to embodied simulations to show how they start to form the cosmic web. So let's start with a bit of the tensions of the colder matter, because you know the paradigm up to now is that the particles are very heavy particles, for example, WIMPs of tens of giga-electron volt, which produce a lot of substructure inside a halo. This is called the missing satellite problem, because observations are roughly about an order of magnitude below the prediction of lambda colder matter. Then we have the core cast problem, which this typical problem that the NFW profile, and it has been shown once and over again, and also we have shown in this Spark paper that statistical fits of many of these galaxies show a preferable quartet profiles instead of Caspi. So this is a very well problem that started like 2 or 3 decades ago, but is still recovering. That's why baryonic feedback sometimes is put on the game, but also self-interactions are put into the game in order to try to solve this problem, and the to fail as well. So one paradigm which attempt to solve this problem is the warm dark matter paradigm. Well, now the non-relativistic relics of cold dark matter I told before are replaced by warm dark matter relics that decouple relativistically, and they have free streaming. So the particles go a given path before again starting to say gravitate in the halo, and then scales below this free-streaming scale, it is said that it erases the concentration of matter inside, and then you don't have this Gatsby behavior, so you have a current behavior. This the fact is translated, or it's better, let's say, shown in the power spectrum. That in the cold dark matter, the power spectrum to larger and larger scale, let's say 10-ish to 100, with very small scales, is always have a lot of spectrum there, a lot of power, so a lot of substructure. But in cold dark matter, due to this free-streaming scale, it's suppressed at the scales, let's say, of 10 to 8, 10 to 7, depending on the particle mass. And therefore, you are expected to have almost no substructure for a given threshold mass, let's say below 10 to 7, 10 to 6 solar masses. Well, another paradigm which is put into the game recently is self-interacting dark matter. This is interesting because it has been shown that in this picture of the bottom left, that with different self-interacting cross sections, typically of order 0.1 or 1 centimeter squared per gram, which are obtained as well as when comparing with galaxy clusters collisions, the Ballet class typical as Ballet cluster constraint. The simulation show that now in this with this self-interaction, which are the plots here in violet and light blue, are much better in agreement with observations of velocities, peak velocities of galaxies at the given scale radius of different scales. While the cold dark matter, as you know, the largest galaxies produce velocity peaks which are much larger than the well, not much, but considerably larger than the spectrum. Therefore, this self-interaction can also be the hypothesis for the dark matter. And therefore, what we have working to put deal with the cosmological perturbation theory. This is the work presented by Rafael Yunis yesterday afternoon, but I will just sketch fast. So we have attacked this problem of evolution of primordial perturbation. So here you have the perturbed metric in the up right. In the synchronous gauge, this is done. With the H is the perturbation. Respect to the Freeman, Lemaitre, Robertson, Walker, and you have the corresponding perturbed Einstein equations with the corresponding perturbation in the matter energy fields. In order to solve the evolution, the time evolution of this linear perturbation theory in Einstein equation, you can either do with fluids, put a perfect fluid assumption for the matter energy, for the equation of state, in order to close the system, or directly with Boltzmann, with the Boltzmann equation, you can couple with Boltzmann. So in order to deal, for example, with massive neutrinos, this is typically done. And therefore, what we have done is couple Einstein equation coupled to Boltzmann here. And therefore, the perturbations in the metric will affect a perturbation in the distribution function, and therefore causing a corresponding perturbation in the matter energy field that you have to solve. Therefore, the distribution function can be split. This is the most general case of Boltzmann equation when you include for interactions, the FDT, right? The most general case. So you split the distribution function in the equilibrium distribution function. So this is typically when particle decoupled from primordial plasma, and then some perturbation F. Interestingly, the perturbations act as a source of the Einstein equation, and you have the density perturbation, which translate into the perturbation in the matter energy tensor, as I showed. So if we have attacked this problem for massive neutrinos of 10-ish of keV particle mass, and therefore you need to first have access to the background distribution function of fermions at the coupling in order to solve this then perturbation theory. And if So when the couples, this distribution function is of Fermi, of this form of F0 is of Boltzmann type here. This is an example, just an example. And so interestingly, in order to know the typical time of the coupling, a rough estimation is that the interaction rate of your particles interacting with the plasma, in this case, has to be lower or equal than the expansion rate of the universe. At this time, when the equality holds, the particles, dark matter particles, cannot maintain any longer its equilibrium and decouples. It can decouple in different ways, in thermodynamic equilibrium, out of thermodynamic equilibrium, and either in the relativistic or non-relativistic regime. So for the standard model neutrinos, it decouples typically, if you want to lead, for example, with thermal relics in thermodynamic equilibrium, but for interactions larger than the weak interactions, so prior in time than typical cold dark matter particles. And interestingly, you can solve an equation for the evolution of the perturbations, and then by making a Legendre transformation of the Einstein equation, you have the famous so-called Boltzmann hierarchies. This is the equation, the coupled equation that you have to solve in order to study the evolution of the perturbations that will lead finally to the is what I was talking about, depending on if the particle decoupled relativistically or non-relativistically. For example, the case we have studied is decoupling from the relativistic regime, but then transition to non-relativistic during radiation epoch, or sometimes closer to radiation matter equality. While this is important difference because in cold dark matter, the particles decouple already non-relativistic, and so all the evolution is much simpler. In this case, which is more general, so when solving this perturbation theory, you can end up with the matter power spectrum, and here is a plot we have recently shown that, for example, in blue you see, yes, in blue is for 1 keV, and in red is for 10 keV. The black power spectrum is the cold dark matter, and you see that, for example, for 1 keV, while standard warm dark matter, so without self-interactions, because as I have told you, we have solved the general problems, including for self-interactions, the suppression is quite pronounced in such a way that this model enter in tension with the substructure and Lyman alpha forest. But interestingly, playing with this different cosmology, you can show that, for example, in the case of a Lagrangian interaction for this matter particle of boson, vector boson, vector boson here, it can be colder, the spectrum, for the same particle mass for 1 keV, and also show without such DAO, so-called dark acoustic oscillations. Well, this is a very interesting, very new field of research, which maybe you did resembles what you may recall, for example, ETOS, the ETOS program of the group of Vogelsberger, which they have in the cold dark matter paradigm, they have a law for self-interactions, but from first particle principles, so not putting a perfect fluid for the matter, just but with Boltzmann equation with these 4 Fermi interactions. And so they have interestingly, they have also this behavior of suppression of the spectrum plus dark acoustic oscillations, and they have shown that these dark acoustic oscillations have impact of the halo mass function on the concentration of halos toward the central region, and therefore this is what we are studying now. What we are studying now in the non-linear regime, and this preliminary result that I'm showing in collaboration with Clément Stahl from Strasbourg University. We have run a suite of different cosmological simulations in self-interacting world dark matter cosmologies, coming from the power spectrum I have shown here for vector boson interactions, and therefore we have run 4 cosmologies up to now corresponding to different power spectrum. These are the details of the simulation, and as you can see, as I was showing, for 1 keV, when you allow for interactions, for specific interaction, your cosmology became similar to cold dark matter. So this you can compare the WDM1 with the WDM1I, which is the interaction for interaction. And therefore, well, this is a preliminary result, which are interesting open game in order to try to, with all these very beautiful but a bit complex as well algorithm that to analyze all the data coming from the simulation. This is a lot of data, terabytes of data that you have to then there are algorithms to analyze, for example, entering in a node and see the profile of your the density profile, the Halo function, analyze the concentration. We are under these studies in order to see if these approaches can also be compared with the halos formed from maximum entropy production that I showed in the beginning of my talk. And yes, so I will go to the conclusions. And so wrapping up all my talk, the main result is that accounting for the quantum nature of the dark matter particles in the relaxation of halos can lead to novel dense core dilute halo profiles. These core halo rare dark matter profiles can explain the rotation curves and stellar streams, while towards the central region, this with the so-called quantum cores can provide a possible alternative to black hole paradigm in non-active galaxies, while probably for active galaxies, the central core should have collapsed towards a black hole. Then for masses between 55 keV and 370 keV, the dark matter, in the case of the Milky Way, the dark matter fermion core can explain the precise astrometric data of the S stars orbiting Sagittarius A star. And interestingly, not yet collapsed dark matter cores are compact enough to cast light image similar to the black hole case. And this is a remarkable result that we have even ourselves been surprised, because we are trying to go as far as we can with this model to see if we really need a singularity or this dark matter can be there at the center. But interestingly, I think it's important to say one and again that it's not trivial at all to have a distribution of dark matter that can, with an Einstein solution of equation, we can account for the rotation curve data and all the way to the center be in agreement with astrometry data of stars and also with the image caused by photons. This is far from trivial result and very interesting, and which I think it be worth it to keep investigating. And finally, as I said, this fermionic distribution can provide a supermassive black hole mechanism formation in the early universe. And finally, cosmological perturbation theory and n-body simulation can be done for these key dark matter particles, including as well for possible self-interactions. Thank you, and
okay. Great, Carlos. Thank you very much for this panoramic view of all the applications of the RAR model. It's very interesting. Are there questions?
May I ask?
Go ahead. Okay.
In these simulations, these cosmological simulations, concerning the self-interactions, these self-interactions are considered in the entire I mean throughout, or you are in the halos. I mean the halos you are considering the self-interactions are everywhere.
Yes,
or in
important
specific parts of the configuration.
Cosmology. Yes, thank you, Jorge. Yes, very good question. So the up to now, the work we have developed here, the self-interaction are only present in the linear evolution of the so in the linear regime of cosmology, because this is because we start solving the Boltzmann when the universe, as you know, were in a much larger density, which much younger, and therefore we solved the kappa latency with Boltzmann with self-interaction. But there, probably I said that some self-decoupling. I didn't put probably yes. Okay, I didn't put the slide of self-decoupling, but the important thing to say, Jorge, is maybe here it is. Self-decoupling, yes. But we have considered in this power spectrum, Jorge, the self-decoupling. So the self-interaction rate at some point overcomes the expansion rate with the late radiation epoch, and therefore the interaction naturally disappear at that scale. So this power spectrum reflects the interaction regime with the matter particles, while the simulation here, the initial condition of the simulation is that power spectrum, which has the effect of interactions, but the self-interaction are not continuously put here all the way until forming the halo. So then an important question that we want to attack as well is to try to see if for a given densities, already when cell gravity enter into game and form a halo, self-interaction again turn on, you see, and then probably in order to fully do this all the way, probably at some point you have to do self-interaction already in the energy body. But up to now, for these weak particles of KV, we have done only until linear perturbation theory, not all the way within the n-body simulation.
Okay, on the same related issue on the self-interaction, probably you said that and I missed it, but what is the self-interaction cross-section you're assuming here? Is it velocity dependent?
Yes.
Is it consistent with the bullet cluster constraints?
Yes.
Maybe you said it, missed it.
Thank you, Piero. Very important question. I didn't have time to put, I didn't say, and it probably should have been important to say this. This is explained in detail in this paper here of Junis et al. This year, where we have indeed checked that our coupling constants, this GD, which are then translated in this CD that you have seen here, probably very small indication. This GD is proportional to the Fermi energy. So this is, you know, the coupling constant to see how order of magnitude larger with respect to the weak interaction coupling constant. And we have checked which order of magnitude of this coupling constant, for which order of magnitude you are in agreement with valid cluster constraints. Yes. And so indeed, the plot here in blue and also in red, both are already in agreement with valid cluster, the self-interaction cross-section, because we have chosen these cases purposely in order to respect that constraints. Yes.
Okay.
But interestingly, just one more small comment that the game is open here because you can introduce different interaction Lagrangians. For example, another very typical used Lagrangian, at least in colder matter, is the light scalar mediator, this interaction Lagrangian here. In that case, yes. So you see, because the coupling of one theory would be different than the coupling of another theory, of course, always allowing for valid cluster, but so you have there different choices to play depending on the interactions you want to consider.
Okay. All right. It's a lot of things to think about. Okay, so any other questions? Otherwise, we are, by miracle, we are in time, on time, thanks to you also, the speakers. Should we then have the coffee break now and reconvene
Yes.
at 11:30?
Yes, Piero, I think it's a good idea. Let's have a coffee break and let's so start with you 11:30, right?
Okay, yes, this is what is written.
Or yes, good, perfect. We start with you, and I will be the chair of the second part
Okay.
of the.
Okay, so I see you in 15 minutes or so. Thank you again,
Yeah.
all the speakers.
Okay, Piero, are you there? Yes, good. I think if you want to start to share your slides, I think we can start the second part of the morning session.
Okay, so so you should see it now. Okay, so
Go ahead. Thank
this talk we have quite a bit of overlap of what Carlos was saying, although it's observation oriented, showing the great advances that have been made recently in modeling the mass distribution of galaxy clusters with very precise strong lensing models. Then some of the consequences of this work, particularly on the subject of the masses, the inner structure, the inner mass distribution of clusters, and the comparison with cosmological simulations. This will be described in detail by Massimo Meneghetti in a later talk. So let's move then, a very brief introduction. So we know that clusters are, at least clusters in the local universe, are the product of the mass assembly of mass on large scales. This mass assembly is driven, as we know, dynamically by the dark matter, which makes most of the mass of these clusters. And by redshift 2 or so, clusters, depending on their mass, clearly virialize and they glow in X-ray. And afterwards, they have a more kind of a passive, if you want, evolution, both for the baryonic contents and the stellar contents, as well as the final assembly, which leads to the creation of very massive systems, like 10 to the 15 or more solar masses. So, as I said, a great advantage is that if we want to study dark matter makes up most of the budget, the mass budget in clusters, but also the baryonic content, which is about 15%, mostly dominated by the hot gas. The baryonic content in clusters is fully observable. That's the great thing, because again, the gas is heated to X-ray temperature, and the stars can be observed in the galaxies. So that, in a way, we have the full pie that can be investigated with different methodologies. And obviously, we'll concentrate here on the gravitational lensing for the course. So going back to already some of the issues that Carlos touched on, what is the interest in trying to derive in detail the structure of these dark matter halos, which we know they are the largest bound dark matter halos in the universe. Well, in a way, it's a way to test the prediction of LCDM, specific predictions on the density profiles of both the dark matter and baryonic components, is also details on the inner structure. So how much substructures there is, what is the population of subhalos which are attached inevitably to the cluster galaxy during the formation process. And also, although indirectly, study the collisionless nature of dark matter as already Carlos alluded to show, in studying, for example, the effect of self-interaction cross-section can have on the inner core, the mass distribution on the inner core, and also possible offsets between galaxies, which are collisionless, and dark matter, which in this case would behave differently from the stars. And also, with very good data, one can also investigate no standard gravity theories, again, studying in detail the mass distribution in clusters. So we've seen that standard lambda CDM simulations have produced this Navarro-Frenkel-White-like, it's just a fitting formula, profiles with generally with a Caspi halo, although the Caspiness of this halo, the core of this cluster is modulated by the baryonic effects. So let's then see how we can investigate this. Well, obviously, we know from GR we have two ways of probing the potential around clusters, well, around anything, in fact. One is using stars to probe this potential. The other is to use photons, which is gravitational lensing. So in a way, by tracing the trajectories of different statistical methods of stars or the gas in case of the X-ray, or looking at the trajectories of photons, we can recover the detail of the gravitational potential. If you're lucky, very lucky, and we happen to have a transient source in the background of these clusters, then we can even probe, if you want, the space-time curvature around these clusters by measuring the time delay induced in multiple images which are created in this case under particular circumstances. And so in the end, the best method to actually recover and study the mass distribution of clusters on a very wide range, basically 3 decades in radius, is to combine all these methods. There is no other way, not only because each method is sensitive to different radial intervals. Typically, if you want to probe the very, very inner core, where often the brighter cluster galaxies are, you need to use the stellar kinematics, but then you can use strong lensing for most of the core, and weak lensing and other dynamical methods, if you have good data, of course, to probe the outskirts. Here in this talk, we'll concentrate mostly on the inner part. Okay. The reason why we want to combine all these methods, because each of these methods has different systematics, inherent astrophysical systematics. I mean, lensing doesn't care about the status, the dynamical status, the matter, but he can be affected by projection effects and so on. Other methods instead are less sensitive to projection effects, but do rely on equilibrium, adjustative dynamic equilibrium. And so, but the cores, the special interest is in the core is that they are particularly sensitive to dark matter physics, and again, the effects, the back reaction effects. So this, I would say, the great progress that we have made over the last, I would say, 10 years is that thanks to coherent programs, especially with Hubble, and then coordinated with the spectroscopic programs on the ground, typically here we show the VLT, one can really, we were able to make a transition from, okay lens models, which are okay for an overall mass distribution description, to very detailed mass models, which produce really high resolution maps of, dark matter maps mostly, but, total mass maps, but then you can subtract the baryonic component to recover the dark matter mass maps. And these maps can be, the detail of this mass can be compared with simulations. And as I said, Massimo will further talk about this. The other new field, if you want, that such a high precision strong lensing models have opened is the way of doing cluster cosmography, doing cosmography, so measuring both the expansion rate of the universe, h0, and the underlying geometry of the universe, using time delay methods like the ones that are being exploited a lot on the cluster, on the galaxy scales over the last years, over the last 10 years, okay? Then, you know, I'll just touch on this at the end of my talk, but I mean, this is again, it's a byproduct. Once you know the lens so well, like any kind of lens, then you can use this lens to magnify, amplify the distant universe, or use these clusters as cosmic telescope and recover the intrinsic parameters of sources which happen to be strongly lensed, okay? Because clearly, without those models, it would be difficult to then effectively use these clusters as cosmic telescopes. So I'll come back to this at the end of my talk. So just to show you what has been the, well, again, the observationally, one always think about Hubble, you know, when it thinks about lensing, because he produces all these wonderful images with, you know, arcs and multiple images and distorted background images and so on. However, to really achieve this, you also need something which is less spectacular, but extremely useful and in fact essential, which is extensive spectroscopy. And so we've been doing this over the last decade, and clearly an integral field unit like MUSE, which was installed on the VLT, what looks like 8 years ago, and it was really a game changer, because at that point you have an instrument which with a 1 arc-minute field of view, which can deliver a spectrum in each pixel. So we're basically in one shot, you get 90,000 spectra. And so often these strongly lensed sources are very faint, you know, they're not even visible in Hubble. If they have emission lines, that can be, even if they're very faint, they can be measured, detected, and the redshift measured with MUSE. So this has been a game changer. Then you can also use the kinematics from the clustered galaxies, and they had, as I show, important constraints on the subvariable population and so on. So these days, clusters with more than 100 multiple images and lots of spectroscopic confirmed clustered galaxies are, you know, are quite normal. Although, you know, a few years ago this was just a dream. And so a program like CLASH or, you know, combination of HST and VLT spectroscopy, although the programs which have actually driven most of this, originally at least most of this progress, and then a subsample of this, or actually a subsample of these clusters have been studied in detail in the so-called Hubble Frontier Field program, which is again deeper observations in both ACS and Wi-Fi camera 3, so up to the H band of these clusters, with the aim of really, in this case, big lenses were selected with the aim of finding primordial galaxies and the highest redshift objects. So just to give you a feeling of what the data look like, at least from the spectroscopic point of view, spectroscopy means that you can, you know, separate the clustered galaxies or the cluster itself from the rest of the galaxies in the field. This is obviously important if you want to do anything, and then you can study both the outskirts and the inner core. In this case, the inner core is MUSE, the inner arc-minute, which is more or less 700 kiloparsec across at this typical redshift of 0.5-ish of these clusters. Then, you know, you have a pencil beam look into this cluster's core, okay? So what is the methodology which is used to recover these mass maps? This is the realm of, is the art of strong lensing, which basically is you have to invert. It's an inversion method if you want. You have to use the presence of multiple images. There can be 2 or 3, 4 or 5 images by the cluster. And then in this case, the one we use is a parametric reconstruction. So you see that you can model the halo, the cluster scale halo with 1 or more, 2 or 3 mass distributions. Typically, pseudo-isothermal ellipsoids are used, which, for which you have as free parameters, you have the central velocity dispersion, the core radius, and the position angle, obviously the ellipticity, and this is one component. Then there is a second component, which is instead describes the subhalo population. Subhalos are all the small halos attached to each cluster galaxy. This is why it's so important to know what they are spectroscopically. And these typically also are used, in this case, spherical pseudo-isothermal sphere are used which are truncated. So you have the central, again, the velocity dispersion and a truncation radius for these as a free parameter. Then for example, some external shear is generally used. And then if you have Chandra data, you can actually use as a prior the distribution of most of the baryons on cluster scale, which is the hot gas revealed by Chandra. So you can model this. I mean, you can observe this and just plug it into the model, because this is, even though it's only 10–15% of the total mass, is an important contribution to the cluster scale distribution. So at the end of this, you can, as I mentioned, this is work that Piero Bergamini did for his thesis in 2019, and then now it's a postdoc in Milan. And what he did for his thesis is try to include the information on the inner kinematics of cluster galaxy to to basically reduce some of these degeneracies in these models, because clearly measuring the velocity dispersion on each galaxy is something the MUSE can do, and means also constrain the mass and the truncation radius of these cluster galaxies. So in the end, you can measure scaling relations like this one, which is basically the rejection relation, L to the sigma square. But this is observation. So this scaling relation can be included into the model as opposed to just fitting it. Okay, so that's an important contribution to the subhalo component of the cluster mass distribution. So at the end of this, you minimize, you vary all these parameters, and you try to minimize the distance, the difference, if you want, between the observed multiple images and the one predicted by the model. Okay, you minimize this chi-square, and at the end of this, you get the parameters, the best fit parameter of the model. You do all your macro chain modeling, of course, to quantify the covariances and so on. But at the end of the day, you get these mass maps. And most importantly, for other applications, these maps come with, these are the convergence, the magnification, all the byproducts that a lensing model can give you once you have the mass distribution. So for example, you have magnification maps for a given source redshift associated to these mass maps. And this is very important if you want to, again, use these clusters as cosmic telescopes. I mentioned how you can reduce the degeneracy. This was an important contribution, as I mentioned. Once you measure the velocity dispersion, you can see here, the red is the model. This basically still a population of these galaxies, and the black are the data. even for relatively low signal to noise, you can measure good velocity dispersions. And you see, in the end, what velocities, what this does is that basically, since sigma square is GM over R, as we know from the Invariant theorem, in a way you can, there is still an inherent degeneracy between mass and radius. This is inavoidable, of course, every time you measure just in mass, but you definitely reduce significantly the degeneracy between the normalization of that scaling relation that show and the and also the normalization of a scaling relation, analogous scaling relation for the truncation radius. So here it just shows like models. This is, you can see in red and blue, these are lens models without any information on kinematic information on the cluster galaxies. And you see that sometimes you get double solutions here, okay, between the normalization of the velocity dispersion, normalization of the truncation radius, and or you can even get bias, this blue bias value. Instead, if you then combine, if you include kinematic information, you can reduce significantly this possible systematics and degeneracies. So at the end of the day, if you do this, you get typically models with more than 200 independent constraints that typically 25, 30 free parameters. And in this case, at least, this is one of the lenses which we have modeled, which is one of the best known lenses because the largest number of multiple images has been identified. And this, progressively, as we use better and better spectroscopy, we discover more and more multiple images, 102 back in 2017, the seminal work that Gabriel Camigna did. And then with Piero Bergamini work, we got to 122. And now these days we have identified 235 images. This is absolutely a big record, in terms of, so having many multiple images, meaning having robust and high resolution mass maps. Okay, so this just is an appetizer for the work, for the talk that Massimo will give. That basically, already in the early work, we noticed that there was something weird when we compared the velocity function, if you want the mass, the velocity function of these subhalos that you can derive from this model with those from simulations. And basically, subhalos for a given mass, they seem to have, the observed one seems to have a larger circular velocity than the ones produced in simulation. So this was already pointing to some tension between the compactness of these subhalos compared to simulation. But as I said, Massimo will deep into this with much more detailed work. So we know that this is 10 years ago, people were very excited about deriving the inner slope of the mass distribution of clusters, because this has an impact modulo, that's the problem, the baryonic effects, which it's hard to model, that this has an impact on the collisional nature of dark matter. So in other words, if the dark matter is collisional, you tend to have cores, okay? But you tend to have cores also for several configurations, several effects of the baryons. So it's difficult sometimes to decouple the two things. But I mean, work already started 10 years ago in measuring the inner slope, the inner logarithmic slope, which you see is not one, it's shallower than one in most of the clusters. There is a scatter and so on. So this work was using data which were far from, the quality of this data wasn't even comparable to the data I just showed you. So as usual, once you get better data, much better data, then you understand the problems that you had when you didn't have better data. And this is typical in observational physics and cosmology. And so we looked into this. I mean, just to cut the story short, even for a cluster where you have an incredible large number of internal radial images, you realize that you definitely measure shallower dark matter density, mass density profiles compared to NFW. But then the interpretation of this in terms of dark matter becomes difficult. And also you understand that the determination of this, even with very good data, the determination of the inner slope, it's at the accuracy that is needed is not as good as you might think of. But I mean, we are getting there. What I'm saying is we are improving this every day, basically. Okay. So again, this connects to what Carlo was saying about alternative dark matter models. Similarly, you can use possible offset between the distribution of the dark matter from the lens model and the distribution of the stars, basically the galaxies. And even there, you have to be careful. I mean, they've been claimed in the literature where dark matter is collisional because they found this offset. But again, you have to be careful because these are parametric models, there are projection effects, and we have done things carefully. And even in the best cases, we never found anything very compelling in terms of an offset. So as far as we are concerned, we don't have any strong evidence of from this, at least from this phenomenology of non-collisionless dark matter. Now let's, as I said, let's move now. I want to move to a new field, but again was opened by these high precision models, which is the extension of time delay cosmographic measurements to clusters. This is a field which is well developed on galaxy scales. Just remind you how it works. I mean, basically, you have to be lucky that you have a source just behind, very close, projected behind, close to the cores of one of these big lenses. And then if you have multiple images, and if this image happens to be a transient source or a variable source, then you can measure the differences, the time delay differences between these two sources. Different time delay, which, as we know, is due to the combined effect of a simple geometrical delay and a more important Shapiro delay due to the lensing potential, of course. So the time delay, as you can see here, then is a measurement. It depends on the ratio of three distances. This is the so-called time delay distance. And so this ratio of three distances clearly scales like h1 over h0 for a fixed cosmological model. And so this has opened the way, has originally envisioned by Radial, to measure h0 with time delay measurements, provided, of course, provided that you can model accurately the mass distribution, which gives you this potential here, which produces, again, the Fermat potential, okay, and then you can make the prediction about the delay, except these h0 values. But it's very important to have these precise models. Now, for clusters, you have another advantage, since if you had galaxies, in a way, the mass distribution of galaxies is relatively simple. However, you just typically have one source, which is lens. For clusters, you have additional advantage. You have many, tens of sources at different redshifts, okay, which are lensed and multiple lens. So you can use the distance ratios to actually, in the distance ratios, h0, they don't depend on h0, but they do depend on the cosmological parameters, okay, on the underlying geometry. And so the combination of these two things can allow us to potentially to measure both h0 and the cosmological parameters. And again, the most important thing is that you can measure, you can model the mass distribution. But I show you that in some cases, we can do this quite accurately. So this is, as I said, this is work which is well developed for cluster galaxy. There is this well-known Holy Cow project, which in a way is a third method compared to the two main methods to constrain H0, one the CMB, the other being the distance scale. And in this case, quasars, okay, are used multiple, you see quads of double images of quasars are used to measure H0. Obviously, there's a lot of work that goes into this. It's not just the modeling of the mass distribution, but also the monitoring program to measure the time delay, because quasars, they have erratic behaviors in terms of variability. So you have to have campaigns of years before you can measure accurately the time delays between these different multiple images. But at the end of the day, the claim is that if you combine all these methods, you can have H0 measurement with an accuracy of 3% or so. And this is interesting, of course, if you want then to try to see whether we do have a tension between late and early measurements of H0. Now, as I said, not many people believe that this could be done for clusters, but then there was this accident, if you want. So Refsdal had thought about this, of course, back in this seminal paper in '64. And the accident was that in one of these clusters that we were studying, one of these frontier field clusters, you see there is this phase-on galaxy, phase-on spiral, which is imaged 3 times, one here, one in the core, which is completely shredded by the strong lens in the core, and another image out here. These are 3 images of the same galaxy. Now, what happened is that in November 2014, a supernova went off in one of the spiral arms, in the spiral arm of one of these galaxies, producing, you can see also this, this Einstein cross, typical Einstein cross multiple image, because there is not only this big lens, okay, here, but there is also the superposition with the small lenses attached to the cluster galaxy. So, and so at that point, this was a wonderful opportunity to make a prediction when this supernova would have reappeared in the future. This is because even when the data, the spectroscopic data were not there, so the models were not accurately, but they were already good enough to say that the supernova probably had gone off in the past, tens of years ago, in this external galaxy, which is less affected by the Shapiro delay, and instead in this internal galaxy where the Shapiro delay is the largest, you expect the time delay, you expect the photons arriving later. And so in a way, once the spectroscopic data were taken, several independent teams tried to estimate blindly when the supernova would have come, would have reappeared again, okay? So again, to start a long story short, the supernova did reappear after 1 year. And there were different models, different teams which tried to make this estimate. Again, this is a blind estimate because, you can always say there are so many parameters, you can always get things right with strong lensing. But in this case, if you do it blindly, you have to predict when this reappears and where it reappears, okay? So it's not a simple prediction. So we actually, with Claudio Grillo leading this, we were the team which were able to produce the best and the most accurate prediction. And so we're able basically to predict within a couple of weeks when the supernova reappear and where reappear with an error of 0.3 arc second. So this gave us some confidence that actually these models are not too bad. I mean, you can, in a way, it looks like you can constrain the potential, the first derivative of the potential, which is the diffraction angle, and the second derivative of the potential, which determines the magnifications. And so when also the supernova reappear, when it was reobservable with Hubble. And so this is when we try the experiment of measuring H0 with this data. And again, I don't have the time to go into the details, but I mean, already you see these models is able to reproduce, the lens model is able to reproduce the details of the three images of this galaxy where the supernova went off, okay, which the supernova went off around here. This is the model, these are the residuals. This shows you that we can model quite well the potential around these at least these two multiple images close to the core. And so using a preliminary time delay measurement, the final one still has not been published, which was 345 days. Now we know that they can measure this with a precision of better than 2%. We tried the experiment, and this is what we get. Again, not only H0, as I told you, in the case of something that you cannot do for galaxy scale systems, by using the distance, angular geometry distance ratios at different, for sources at different ratios, you can also constrain omega matter and omega lambda, for example, okay, for a general lambda CDM models. And these are the constraints, you see, it's not bad. So H0 is measured, this case, with a 5-6% error. This is a single system, okay? As you see, that also the cluster galaxy, the galaxy scale systems can measure H0. These are these color distributions here, can measure H0 with an accuracy of 7-8%. And then the combination of those, by combining those, you can collapse the error. So this is, it's comparable with this single measurement. But the advantage is that without absolutely no prior on the cosmological parameters, you can constrain the cosmological parameters with, quite well. I mean, even, that was surprised, even W, if you just abandon a lambda CDM, you go to a flat W CDM model, you can measure W with a 20% error, okay? And so this is clearly interesting, and obviously we would like to repeat the experiment. Now, to have another supernova going off behind a cluster will take some time, probably will take LSST to do it, but we can use quasars. So we started, now there are very few 4 or 5 quasars, multiply lensed quasars known behind clusters, and we have started actually searching for them, but in some cases, like in this case, again, we have used Muse spectroscopy to improve our lens models, and now we are in the process of the time delay between these multiple images is measured, was measured by this collaboration with a lot of work, and so we're now.
Sorry, 5 minutes, Piero.
Yes. Okay.
6 minutes. Yeah.
Sure. We are now going after this another quasar. Lensed quasar system by clusters to try to provide additional measurement of H0. Okay, so just to summarize this part, and then I'll touch quickly on the gravitational telescope thing because it's cool, especially because JWST is coming. And so what is the summary about this? I told you about how we can improve a lot on, but again, this Massimo will say more about this. We can improve on constraining or verifying the prediction of lambda CDM models with this kind of data and gravitational lensing modeling. With the same models, the same high precision models, we can always, if we're lucky, enable time delay cosmography with clusters, and then let's see what we can do with gravitational telescopes. Okay, so again, if you have a lens that very well the magnification structure, okay, where spatially, this is, of course, is a very aberrated, it's a lens with a strong aberration, but who cares? If you know the aberrations, then you can use it to explore the distant universe. So this has been done traditionally with the fields with Hubble, okay? The Goods field, it's classical example. Deep fields, you look at, you reconstruct luminosity functions at higher and higher rashes and trying to infer, to basically learn something about the formation evolution of galaxies, okay? Clearly, this has a limit. Now, this limit would be shattered by JWST in a week, but the limits so far is around, well, there are two limits. One is, you know, even if you integrate for a month, it's harder to go deeper than 30th magnitude. The other is that inevitably you are, when you go to high ratio, you have to look at the rest frame. You are bound to look at the rest frame UV when, you know, you would like to look at the rest frame optical, possibly even rest frame near infrared in these primordial galaxies, to really learn much more about the stellar, the star formation history and the formation epoch and so on and so forth, and impeded by dust. And so to go deeper, obviously you can use lensing, and the questions, of course, that everybody has in mind is to search for very low luminosity, low mass means below 10 to the 7 solar mass. I'm talking about stellar masses here, because these are possibly the pieces which then came together to make the first primordial galaxies. And to access these low mass, low luminosity objects, there is no other way as of today, but it would be the same with JW, because you can still use JW and lensing. But as of today, you have to use lensing. And so again, if you know the lens, if you have these models, then you can recover the luminosity, the intrinsic luminosity, the star formation rate, the masses, the sizes, the luminosity function, and so on. So you can actually use this. This just to show you that how you basically go like a couple magnitude deeper with lensing, with Hubble data, and approaching what JWST in the field will be, okay? But it's always important to remind that gravitational lensing conserves surface brightness, which means that you don't only amplify, but also magnify a distant galaxy. This is very important because we can basically look at very distant star-forming complexes, like under a microscope, down to only really 5 or 10 parsec resolution, thanks to the magnification. If you go, obviously, to a high magnification exceeding 10, high magnification area, okay? So this can be already done with Hubble, and will be done again with JW to push even further. Okay, an example of this is, for example, again, in the same Mirabilis field of where Refstal was found, there was this galaxy that was identified as a possible galaxy redshift between 9 and 10, which then has been confirmed with a redshift 9.1 with the observation of the 88 micron oxygen 3 line with ALMA, okay? And so this is just an example of how lensing can actually unveil really high redshift galaxies. And fair enough. Okay, so I just wanted to prepare a few more slides. This work has been led by Eros Vanzella in our group, and so just to give an example, this is just as an example of how you can, you see, these are objects which are magnified, these red ones, these are redshift 6. And here you can see the intrinsic recovered magnitude. We're talking about 31, 32 magnitude. We have single star forming clumps with an intrinsic magnitude of 33 or even 34. And so we've been studying the physical characteristics of these clumps with, again, aided with these lens models. And for example, you know, from the physical parameters we have derived in terms of ages, sizes, intrinsic, absolute magnitude, and so on, we believe that some of these clumps we have found might be the progenitor of globular clusters, okay? which at some point there must be somewhere, given all the global clusters we have in the local universe. And so I'll just stop here and give the final prospects on this final theme. And obviously everybody's waiting for JWST. Okay, in a week we'll see the first images, and we have programs approved on this lensing cluster. There are several, and so obviously, you know, we're all excited to see what JWST will reveal in this highly magnified area of the sky, and this will give us a lot of input about how we can use the extremely large telescopes to actually study the primordial galaxies. And for sure, you know, there is LSST, Euclid, all this wide area service, which will reveal many more big lenses, okay? And so we can do the cherry picking of the best lenses to do this kind of science in the future. So that we'll be busy for several decades, I think. Thank you.
Okay, thanks a lot, Piero, for this talk. Very interesting results and promising future perspectives. So we have time for a couple of questions. Yes, Jorge, go ahead.
Thank you. Thank you, Piero. Really fascinating topic. I have two obvious questions. Say the first is, you really expect that the new data from the James Webb telescope will improve the calculation of the mass profiles in the inner part. I mean, in the improvement in the estimation of the slope of the density profiles. The second question is, why an exercise like the Revsdal one cannot be done with the optical afterglow gamma ray burst?
Right. Very, very good questions. Difficult to answer. I mean, the first one, I don't know, nobody knows. I mean, for sure, we have even tried to estimate what would be the boost in the number of multiple images with JW. But, you know, JW is going into, now it's true that you don't need to go to very high redshifts to improve on these images, on these multiple images. Most of them are actually a relatively low redshift between 2 and 6 and so. And after all, the volumes that you are magnifying are relatively small, so you need to have galaxies in the background, and so it's hard to know. But for sure, there will be many more multiple images, and possibly in the core. And the latest thing, you know, rumors are that the PSF of JW it's even better than what was anticipated. As this will help in detecting extra multiple images very close to the core in these clusters. Some of them is true, they will need spectroscopy, but you know, JW has spectroscopic modes, so for sure this will come. But if you ask me how much is a factor 2, 3, 5, it's hard to tell, but for sure this will come. So GRB, yes, so we have actually tried, we had a student, we have tried with Cristiano Guidorsi to quantify what are the chances. That, as you probably know, there have been several claims. No one, we believe, is really credible. I mean, at least, but there are several claims that of lens GRB, and at some point there should be this this kind of events. It's just a matter of, for example, with Theseus, you know, the number of GRBs was going to increase so much that we were expecting possibly several of these events. At this point, I don't know. We need to keep working on the models. We've started doing this, but I mean, not to the detail that is needed to really make robust predictions. But it's definitely a possibility, and it's quite exciting one, in fact.
Okay, thank you, Piero, for the answers.
Is there any other question in the audience? I don't see raised hands. If not, I have a small question regarding the Radial reappearance of this supernova. This very nice result you shown. Which is the degeneracy you have between the H0 and the free parameters of the mass models you are used to generate the wall length pattern?
Yes, well, yeah, for sure. This error that you see here, they come from the Markov chain exploring all the free parameters of models. Plus, we investigated systematics, okay, at least some of the systematics, and one of these has to do with the so-called match degeneracy. So if you have something, along the line of sight, this obviously bias the mass distribution and linearly bias also the measurement of H0. Again, the fact that you have multiple images at different redshifts in clusters helps you quite a bit in alleviating the so-called mass degeneracy, which instead is a primary problem and a source of systematics for galaxy scale systems. So these are the errors you see here comes from the model parameters. Then we check for this also other systematics, and this move these contours by something which is less than the statistical error. So it's no more than 1%, okay? But the statistical error is still, 5–6%.
I see, Piero. Okay, but so these probabilistic control plots or errors you are showing are from cosmological parameters. But I was referring also.
Right, but they are in there. But in there, there are the errors. There is a covariance matrix coming from the 30-ish. I don't remember exactly. The 30-ish mass parameters are in there. The fact is, for Radial, this is why this is not. It can be done only in very particular. The fact that here you have the constraints are so strong because we are using as multiple images all these knots. They are like almost 90, 80 knots of these. You see these star-forming regions, and you can identify these star-forming regions in these phase-on spirals in this image and the corresponding one in these images. So this constrains very strongly the mass distribution in this area where the event occurred. And this is why in this case, the model is nailed really accurately, and the Markov chain exploration of the mass parameters produce, acceptable errors. Now, if you were to do this in another cluster, not with this, you would get 15%, 20%. I mean, it would the contours would be much larger. Here, it was a fortunate case where you have a lot of constraints, okay, around the event. This is not, okay, this is why I said you need to wait and you have to wait for another, you have to be lucky. So
I see.
Principle with LSST and Euclid, especially LSST, other of these systems, and again you can use quasar, but it's not something that you can do it every day.
Okay, thank you, Piero. Yes, I will probably leave the other question to Massimo, which are related, because we are a bit off on time. So yes. we really thanks Piero again for this nice talk. And we have a lunch break now, and we will go back after lunch break in. So now it is 1, 2 with the first talk in the afternoon. So with Massimo Meneghetti. Okay, thank you all, and see you after the lunch break.